This is a short review of the basics of machine learning. We know that the field of artificial intelligence, the whole field of artificial intelligence, includes machine learning as its subset. There are some methods beyond the scope of machine learning in artificial intelligence, but the machine learning is really a part of today's methods of artificial intelligence. So, machine learning is a subset of artificial intelligence, and in turn, deep learning is a subset of machine learning. And we will talk a little later about it in more detail. So let us consider basic types of machine learning. Of course, the main two subdivisions are supervised learning and unsupervised learning. Also, semi-supervised learning, intermediate position, and reinforcement learning are also prominent. But basically, we are concerned here with the supervised learning when we have labels for our training data, and unsupervised learning when the data are unlabeled. So, what's the basic difference between supervised learning and unsupervised learning? In supervised learning, we're given the labels of our data. In unsupervised learning, the data are unlabeled. So, what we can do in the case of unsupervised learning, we can try to understand the structure underlying the data, and also classify in subsequent, in the future, classify new observations. So in unsupervised learning, the data are not labeled. In turn, the supervised, now we'll consider in more detail the supervised learning. There are regression methods and classification methods. What's the difference? In regression, the predicted variable is continuous, like a price of some product or temperature, some climate conditions, etc., consumption of a vehicle in the examples which we considered in previous videos. And classification means that the predicted variable is of a discrete nature. So, for example, we want to determine the belonging of some object to a particular class. So, in regression, first of all, we must know the linear regression, where we have some data and we want to build a line, linear dependency, which approximates our data points in some optimal sense. So, y hat is wx plus b is a most straightforward way of approximating our data. And the task is to determine the parameters w and b. That is to train the linear regression model. This is univariable, where only one variable x is present. But when we are given some set of input features, then we have predictions. We have predictions, which is dot product of some fixed weight vector w and input feature vector x plus b. B plays the role of a bias. Bias, or sometimes it's called intercept. A free term b is like a constant bias which moves our prediction. So in this case, the prediction is formed as dot product of w and x and plus some constant shift b. And the training of such a model lies in the determining of parameters w and b, again, in some optimal sense. A little later, we'll consider what criterion can we use. And the most popular and most convenient criterion for this purpose is a mean squared error, a cost function, where we just finding the w and b, which minimize the mean square difference between target non-variable and their predictions wx plus b, or dot product wx plus b in the case of multivariable regression. And fortunately, this function in the case of linear regression, both univariable and multivariable, is convex function as is shown here. And it has one minimum which can be found even analytically. Also important is the scaling of parameters, removing zero mean and dividing by standard deviation. So this scaling is essential so that our cost function will have a distinct minimum. Maybe for analytical solution, for closed form solution, it may be not so essential, but for application, for example, of gradient descent, it could be quite essential for all the variables to have approximately the same range. And as I said, gradient descent is the most popular way to find the minimum point of cost function. And this sense is that we're changing our parameter theta, which includes coefficients w and b. We are changing it by the weighted gradient of cost function. Gradient of cost function means a set of derivatives by all unknown parameters. In our case, it's w and a set of w's and b, return b. So we are moving our parameters in the direction which is opposite to the gradient. It means that theta is updated as theta minus learning rate alpha multiplied the gradient of the cost function. Learning rate must be carefully selected so that algorithm properly converges. It should be selected adequately for each particular application. And in the case of linear regression, both univariable on the left and multivariable on the right. No, I'm sorry. These are the equations for the case of univariable linear regression. How W and B are updated based on the gradient of the cost function, which is calculated here on the left. So quite simple equations. And we can see here also that here implicitly the error of estimation is present. Wx plus b minus y is the error of prediction. Yes, and it is present when error is 0. Obviously, w and b are not updated. So, learning rate alpha, as I said, must be carefully selected. If it's too small, the gradient descent converges very slowly. If it's too large, it may be quite fast, but it also may diverge. As shown, for example, here on this example, where the cost functions versus the number of iterations is shown, and for very small alpha, the gradient descent converges very slowly. For a larger, for medium size, it converges a little faster. It can converge very quickly, very fast convergence when there is a large value of alpha learning rate, but it could be very large. When we take alpha very large or too large, it starts to diverge. Here on the x-axis is the number of iterations. So it must be carefully selected. What for the case of nonlinear regression? Nonlinear regression is very interesting. Here we are trying to approximate our target values by a polynomial function of input feature vector x. And the idea is that we just take the different powers of x as a new variables and apply the multivariable linear regression, as we have shown previously by the same methods. So we just consider x squared, x cubed, x to fourth degree as a new variables, and we apply the methods of multivariable linear regression. So when the order of polynomial is quite low, as in this example, the approximation could be quite poor. It is called high bias or also underfitting. For example, when the first degree of polynomial, that is simple linear regression, or for second degree of polynomial, this is like quadratic regression, approximation is still quite poor. And this is called high bias, when even on training data, we have a large prediction error. But the opposite is for high degrees of polynomial, when we have perfect reconstruction of training data, but we have at the same time we have a very large error on testing on independent test data. Yes, this effect is called overfitting. Very large error on test data, a very low error, although very low error on training data. This is called overfitting. And also we observe that construction of such polynomials for high order approximation, polynomial approximation, leads to the values of W, as shown here on the left bottom corner, values of W, which are quite large in magnitude. So the problem becomes, our problem of estimation of parameters W becomes unstable. The parameters W, B is not usually growing so significantly, but W start to grow. And this leads to high variance or overfitting. So also we can see what resulting graph of test error and training error we have. with the growth of polynomial degree, training error decreases and test error significantly increases. It significantly increases, and this is obviously due to effect of overfitting. Although for low orders of polynomial, they are quite similar. Even sometimes training error could be a little higher, but this may be due to not sufficient averaging of results. But the general tendency is that with the growth of polynomial degree, the test error starts to grow exponentially, which of course is not good because we are interested in the algorithm which generalize well. Generalize means such methods provide good predictions for never seen before data. So what can we do in this situation? Again, we could face a high bias when even for training data approximation is quite poor, and high variance when especially for testing data the estimation error, prediction error is very high. How to deal with high bias? High bias when even for training data we have better approximation. We can try getting additional features. We can try polynomial features. If also we may note that getting more training data usually does not help much. What can we do with high variance? Well, we can get more training examples. We can try smaller sets of features or lower order of polynomial. And also we can try regularization. I will briefly explain what regularization means. Recall that we observed growth of parameters W in value, which followed the growth of polynomial degree. So we want to penalize the quick growth of the values of weight coefficients W. How can we achieve it? We achieve it by regularization. It means we extend our cost function with additional term, sum of squares of coefficients W. It means that we are simultaneously trying to make lower approximation error Wx plus b or dot product Wx plus b minus y, target variable y, and also we try to minimize absolute values of W. And this is also called ridge regularization, like ridge which cuts the waves in the ocean. So we're trying to damp the uncontrolled growth of weight coefficients W. And here, in front of this sum of squares of W, there is a regularization parameter lambda, which also should be carefully selected for each application. Due to this addition of this square term into our cost function, the update equations for gradient descent are slightly updated. Equation for B, for the update of intercept B, remains unchanged, but the equation of W slightly changes by this W divided by M. M is the number of observations, or it could be also included into this lambda divided by M, multiplied by corresponding value of weight coefficient I. So for each coefficient, we have additional little term for the update of W. And obviously, when lambda is equal to 0, there is no change in comparison to usual multivariable linear regression. We get the same equations. So what is the effect? What could be the effect of such regularization? For example, without regularization, on the left, we could get a very low training error and very high test error at the same time, which is not satisfactory, of course. But considering regularization with a lambda of 1/10,000, we get much better approximation, both some compromise, balance for the approximation between training and test data. Test error is 0.2 and training 0.25 and training error is 0.13. So it's a good compromise, obviously, in this situation. With the same lambda of 1/10,000, we can see on the right what is now the behavior of test error, of approximation error, both for training and test data. So its behavior is much better as compared to the non-regularized case on the left. You can see obviously the difference. This is the effect of regularization. So also important, what I would like to know is always, when we are dealing with any machine learning problem, we divide our data onto training data and test data. We train model on training data, and this model is expected to be well generalized. It means that it should perform well on test data which were never seen before when the algorithm was on the stage of training. Also, maybe we also discuss it in other video, which is called validation training data sets. So training data itself is subdivided onto training data, on which the data is immediately trained, and also cross-validation data to tune some special parameters of machine learning model. Please look also on our validation video, which will accompany also this short lesson. Okay, this is essential to understand. So to have some preliminary understanding, we must remember that to deal with sky bias, we can get additional features, try to add polynomial features, decrease lambda, regularization parameter lambda, if we have already used it, or adding more training data usually does not help. How to deal with high variance, or in other words, with overfitting? We may try to get more training examples, try smaller sets of features, and increase regularization parameter lambda. Yes, it's also possible to deal with effect of overfitting. So this is how we're dealing with high variance. Okay, so next part of our review will be binary classification with the help of logistic regression. We have already observed the linear regression, and just to remember, the classification differs that in the way that our predicate variable is now of some discrete class. It doesn't of continuous nature, but it's of discrete nature. For example, we want to predict the belonging of some variable to one of the particular classes. So this is the case which we now briefly consider for our memory. So yes, for example, in the case of regression, we are trying to predict what the temperature is going to be tomorrow, but in classification, just binary decision. Will it be cold or hot? Binary decision. And also, we observed and discussed that linear regression immediately cannot be applied to classification task. Yes, it could also be used, applied to approximate some binary values of variable, but it produces uncontrollably large values, which are beyond the range of 0 and 1, which is not satisfactory, because we're interested not just to classify data onto zeros and ones, but also to get some kind of probability. And for this purpose, we may consider some function which squashes or compresses the range from minus infinity to infinity to the range from 0 to 1. And we told that sigmoid function, sigma of z, 1 divided by 1 plus exponent of minus z, is well suited for this purpose. It has very nice properties also from the mathematical point of view, and it compresses the range from minus infinity to infinity just to a range from 0 to 1. And so, if in the case of linear regression, we our predicted variable was just a dot product of weight w and feature vector x plus intercept b. In the case of logistic regression, our output variable is the application of the sigmoid function to the dot product of wx and plus intercept b. So sigma function, which is in the context of machine learning, in the context of deep learning, it's called activation function. One of the types of activation function is applied here. So this sigmoid function, it compresses the range from minus infinity to the short interval from, not short, it's also of continuous nature, of course, continuum nature, from 0 to 1. And the argument, this argument dot product wx plus b, which is passed to the sigmoid function is also very often called logit. Logit. It's another name. So also, usual mean square error does not work well, especially from the mathematical convenience for logistic regression and for other classification problems. So binary cross entropy. This cost function is called binary cross entropy. It is used for logistic regression. So it just takes, it includes expression which looks much more like entropy from physics or from theory of information. This is a sum of possible variables y and y minus y multiplied by the logarithms of corresponding probabilities. Sigma of wx plus b and logarithm 1 minus sigma of wx plus b. And it can be shown when wx plus b, sigma of wx plus b is close to 1, and also y, target variable, is close to 1, this function is approximately 0. When there is the prediction is very bad, this function goes to infinity. This function goes to infinity, and this is the good indication that this cost function is well suited for our purpose of classification. So this is binary cross entropy cost function. It is used for logistic regression. Equations, as we have also observed, for the logistic regression of gradient descent, when gradient descent is applied to solve the problem of logistic regression, the equations are quite close to the case of linear regression. The only difference is the presence of sigmoid on the left. And again, we see that the error of prediction, sigma of wx plus b minus y, is present. So this is error. And as we have already told, these equations can be quite well vectorized. So here we may observe that we to make just one update of parameter w and parameter b, we take the sum of all errors and their cross products with input feature x over the whole data set, all the m data points which are used for training. When we have many millions of training data, this is not very convenient. And we discussed that some suboptimal approaches are used. So when we use all the data for the update of W and B on every step, this is called batch gradient descent. The completely opposite to it, stochastic gradient descent, is when we update W and B with no averaging. After considering every new training data vector, we compute. In fact, we do not use any sum here or averaging. Without the sum, just W is updated like W is W minus alpha divided by M multiplied by concrete approximation error for this data sample multiplied by input feature X. And this is called stochastic gradient descent. But when the averaging is done on small or moderate batches, not on the whole data set, but we divide our data on some blocks, which are called mini batches. And when the update of this W and B is done after each batch, this is called mini batch gradient descent. Which is some compromise between computational expenses and the quality of performance in the case of pursuing the lowest approximation error. This is mini batch gradient descent. And correspondingly, these methods have different behavior of cost function. For stochastic gradient descent, it is most unstable, like flickering. It's most smooth for the batch gradient descent and some intermediate behavior for mini batch. Realization of gradient descent. This is also how the moving to the point of local minimum can be depicted. Well, also one important parameter, especially in the case of neural networks, the epoch. Epoch means one whole transition through the whole data set. For example, if we divide our training data into some number of batches, when all the batches are processed, this is called epoch. And correspondingly, as many runs through the whole data we use, so many epochs are in our machine learning algorithm. Of course, data could be randomized between epochs, and this is also quite often used to make algorithms to minimize the possible effect of overfitting. Such randomizing between epochs could be some remedy against the effect of overfitting. So this is for classification. Also, when we're talking about classification, what's important should be remembered is that we can build a decision boundary. Decision boundary is corresponds to values of of x, input vectors x, for which sigma function is 1/2. When sigma function is 1/2, the argument of the sigma function is 0. So the dot product of wx plus w dot product of w and x plus b 0 means some hyperplane n dimensional. If we have n variables, n is dimension of our input feature vector, then this is equation of some hyperplane. It is line in the case of two parameters. It's one point, just in the case of one-dimensional logistic regression. Or it could be some plane in if we have three variables. So this, in general case, it's called hyperplane, which subdivides the values of feature vector x corresponding to decision 0 and 1. This is called decision boundary. We also, previously, we considered how this decision boundary could be built for such maybe trivial example, but nevertheless we observed that it works even for the circle. But for the circle, we had to go beyond the usual linear use of linear features x, and for the case of circle, we consider squared features, which provided us also with the adequate decision boundary, which was like a circle line in this case. So the equation for the decision boundary was w dot product of w and squared feature vector x plus b is equal to 0. This was equation for the decision boundary. So what's for multi-class classification? For multi-class classification, by the way, if any questions or comments, please don't hesitate to interrupt me. I'm just giving general overview of the topics which I included into this short course. Please don't hesitate to interrupt me or in any way. So, multi-class classification, what can we do? Yes, the task, of course, seems to be much more difficult, but it can be subdivided. It can be subdivided also onto several binary classification problems. So one of the approaches to solve the to multi-class classification problem is so-called one versus rest. So we must decide if our variable x belongs, for example, if we have three classes, A, B, C, we have such three dilemmas. Whether x belongs to A or to union of B and C, or x belongs to B or union of A and C, and correspondingly C or union A and B. And finally, we must see was the highest probability for which case we obtain the highest probability of x belonging to particular class. So we have to train separately. I believe we have to train separately three different logistic regression models. And then on the base of it, we can solve in such a way by taking the class which is maximum probability across the three ones, we can solve the multi-class classification problem. So alternative, and which is supposed to be more optimal, is so-called softmax approach. So in the case of binary classification, our logistic regression provided us one probability. But there are two classes, 0 and 1. So in fact, there are two probabilities. One is produced by the sigmoid function, and another one is y minus result of sigmoid function. So there are two probabilities. In general case, In general case of k classes, we have to obtain k probabilities. K classes, k probabilities. And all these probabilities should give 1 in sum. When summarized, they should give 1. So how can it be achieved? How can it be achieved? So for each class, we must determine again particular set of parameters w and b. For each class, there should be vector w of weights and intercept b, separate personal for each class. And based on it, we can calculate corresponding probabilities by using, it looks quite close to logistic regression, exponent divided each exponent of each logit divided by the sum of all exponents. And obviously, these probabilities will give 1 when summarized. In total, they produce the value of 1 when we take their sum. Loss function is very similar to the one we used in the case of binary classification, and is called cross entropy. Not binary cross entropy, but cross entropy. Simply cross entropy, simply cross entropy. And it's calculated in a similar way as a sum of y multiplied by logarithm of y hat. Each y hat is a probability of belonging to a particular class calculated by the above formulas. I will not go into the details, but W and B, they are also calculated by the method of gradient descent, and which helps us to minimize this corresponding cost function. Yes, here loss function is depicted for one, means for one piece of data, for one item of data. But when summarized over the whole data set, this is called cost function. As we told, this is the difference between loss function and cost function. Cost function is a result of averaging of loss function across the whole training data set. So, for example, in this case, when we want to determine to which of three classes belongs some particular picture, for example, we have logits, that is wx plus b, 4, 2, and -2 for three different classes. We calculate probabilities by softmax. Yes, exponent of 4 divided by exponent of 4 plus exponent of 2 plus exponent of -2. And we get, for example, for the first picture, for the first item, we have 0.88, which is the highest probability. And the one for the negative logit, of course, has the lowest probability. Yes, so this picture corresponds to a puppy, but not certainly to a rabbit. So in this way, by softmax, we can train our multi-class regression, multi-class classification problem, that is to find corresponding W and B, so that we can calculate the k probabilities for k classes and select the class with the highest probability. This is the idea of softmax approach, which is widely used, especially also for the neural networks, and we have also observed it. What I want to stress before we will go to the general overview of deep learning is that linear regression model and logistic regression model can be considered as neurons. This is like a elementary units of processing information. Like, for example, linear regression, we have n inputs to the neuron, and output is a prediction in the form of dot product of w, weight vector w, and input vector x plus b. So we have n inputs and one output. In the case of logistic regression, the same situation. We calculate the dot product of w, x, and plus b, but also it's called activation function. Sigmoid function, in this case, is called activation function, is applied, which introduces nonlinearity. And also like a simple elementary neuron performing the task of like logistic regression. Yes, also we have to remember the concepts of recall and precision, which we considered when we were talking about the classification, especially binary classification. we observed that just calculating prediction classification error as a number of wrong decisions divided by number of total decisions is not proper way of calculating the quality of estimation algorithm, especially when the data set is unbalanced. So, for example, a completely different balance between the values of y and zeros in our data. So it doesn't produce proper results and may lead completely to misleading impression about the quality of classification method. For this purpose, we introduced precision and recall. Precision and the number of true positives divided by true positives plus false negatives, and corresponding recall true positives again divided by true positives plus false negatives. And this terminology corresponds that true positive means actual value is 1 and predicted is 1. Or for example, false positive, in fact, the target variable is 0, but we predict the value of 1. It means that the number of false positive will be increased by 1. And finally, when after processing over the whole test data set, we obtain these parameters recall and precision, which characterize the quality of our method. To find the total integral characteristic, because there is sometimes there is a we must find the compromise between precision and recall. In particular, we have to select a proper threshold to compare with which sigmoid function will be compared, because all equations for gradient, descent, etc. doesn't depend on the value of threshold. The threshold of 0.5 is most logical and is most commonly used, but it's not the dogma that we use only 0.5. When, for example, we want to get high precision at the cost of possibly low recall, we can increase the threshold. And correspondingly, to get the high recall, we may make lower our threshold, for example, 0.1, like in this case. So, what I wanted also here to mention, that yes, high precision means that, for example, if we're detecting the presence of some disease, high precision means that if we predict the presence of disease, there is a high probability that the patient really has it. And high recall means that if there is a patient with that rare disease, there is a high probability that it will be identified. Yes, there is a little difference. Sounds almost like the same, but there is a difference. In the first case, if we predict the presence of disease, then the patient has it. In the second case, that if there is a patient with disease, with high probability, he will be identified. This means high recall. It means the false negative decisions are almost zero. The total number of false negative decisions is almost zero. This means high recall. To take a balance of them, we introduce the F1 parameter. F1 is calculated as a harmonic mean of precision and recall. And for example, to compare between three algorithms in this case, although the mean value of precision and recall is the highest for the third algorithm, it is most poor in the context of F1 criterion. F1 is the highest here for the first algorithm, which has precision and recall 0.5, 0.4 correspondingly. So F1 is like some integral characteristic for the performance of estimation methods. Of course, especially it has sense to use it in the case of unbalanced data set, which means that number, for example, of zeros and ones is not the same. Well, for multi-class classification, also there are it cannot be directly applied, F1 and precision and recall, but there are some approaches also to introduce similar, more generalized parameters. But basically, this is for the case of binary classification, precision and recall. Also, there is a concept of precision recall curve, when we select different possible thresholds and build corresponding and plot corresponding values of precision and recall, which are depicted here by blue dots, connected with the blue line. Sometimes it is said that we can select the best threshold, the one for which this vertical distance d between our precision recall curve and the line which connected the points 1, 0 and 0, 1, this distance d, when it's the highest, it is it's very often tells about the best threshold. Like, for example, also here in this case, both d and f1 parameter produce the same value of threshold, approximately 0.45. So we can select optimal threshold for our classification problem by analyzing this precision recall curve. So can we move further to the basics of deep learning and our short review? Deep learning is a subset of machine learning techniques. What's the feature of deep learning? The characteristic feature of deep learning. Deep learning uses neural networks trained by special algorithm. So neural network is a combination, superposition of many neurons, which are organized into layers. And usually it is supposed that each layer is connected with all the, each neuron in each layer is connected with all the neurons from the previous layer. Sometimes it's not so, but this simply means that the corresponding weight coefficient of transition from one neuron to another is 0. But basically we can plot that all of them are connected with each other. There is an input layer, which nevertheless is not considered as a layer. Usually it's just a set of input data. For example, here in this case, it means that we have 4 input variables. And at the output of this network, we also have not necessarily the same number, but here we have 4 output parameters. For example, corresponding to probability of some picture belonging to one of the 4 possible classes. This is the idea in very general, idea of subsequent processing information by the neural network. And deep learning means using for classification or regression or other tasks the such networks with a high number of layers. Basically, the word deep means of course, deep intrusion into the understanding of the underlying structure of data, and deep also means that many layers. There are many layers, and the depth of the model is the same as the number of layers. Also, we talked that the deep learning is also called feature learning. It means that each subsequent layer of neural network provides us higher level of representation of data. And finally, we're supposed to, on the final layer, to make a proper decision of belonging of our object to the necessary class. In the case of classification, in the case of, but most often deep learning networks are used for classification purposes. So each layer provides another level of hierarchical level of representation of information, of input information. Also, we mentioned the analogy with distilling. Information is subsequently purified with each layer. More or less, with each next layer, our vague understanding of underlying data increases, improves, is refined, and we get the proper final correct decision at the last layer, at the output layer of our neural network. So again, each neuron, as we have already told, usually makes a very simple operation. It's a gain. Again, the same dot product of wx plus b, where x is a number of parameters which come from the previous layer to this neuron, and activation function g is applied to them. For example, g could be sigmoid. Most often used activation function is the same sigmoid, 1 divided by 1 plus exponent of minus z. And this is the output. This is the output of neuron, which correspondingly goes as the input, serves as the input of other neurons of the next layer. So this is what each neuron does. So activation function, yes, in more general case, activation function is any function could be used as this nonlinear function which is applied to this, let us say, logit wx plus b. But logit probably is more for just for the case of logistic regression. Just for the case of logistic regression. So activation function, generally any function, any nonlinear function can be used. And it's applied to the input of weighted sum of wx plus b. Several types of activation functions are usually used. Linear activation function, which is simple linear transformation, multiplication by a constant, or maybe plus sum also intercept b. Sigmoid function, about which we have already told. It can capture some complex patterns, of course, in comparison with a linear function. Output values are bounded, which is beneficial, as we have already told, but it suffers from so-called vanishing gradient. I think we will say a few words about vanishing gradient also. Hyperbolic tangent, very similar in behavior and also quite attractive from the mathematical point of view, activation function. Its range is not from 0 to 1, but from -1 to 1, which is also such centering. Sometimes is also beneficial, but generally it suffers from has the same drawbacks or as a sigmoid function, because very often for most of its input variable, the gradient is almost 0. This is the so-called problem of vanishing gradients. And function completely different from them is ReLU. ReLU function, which is a maximum, ReLU of z is maximum of 0 and z. So it has 0 values for negative. It has 0 value for the negative input parameters, and it's linearly dependent on the z for positive values of z. So very often it is also used, especially at the intermediate layers, hidden layers, which are called hidden layers of deep neural network. It also can be used at the final layer, especially when we are predicting some positive value. For example, the price of the house, for example, also it cannot be negative in any way. So the such ReLU function, or some combination function, of course, with a proper selection of w and b could be used. And yes, this is a short review of these functions and activation function and their derivatives. We also must be very careful which activation function should be used. It depends on the type of the problem that we consider. For example, in regression, final activation function should be linear, or maybe ReLU, and mean square error is considered as a loss function. In binary classification, we use activation function as a final layer sigmoid, and binary cross entropy cost function, loss function. Doesn't matter, lost cost in this case, no difference. Just averaging of the whole data set in the case when we say cost function. And in the case of multi-class classification, at the final layer, we have softmax and cross entropy loss function correspondingly. So this is what we must remember, even if we do not remember mathematical formulas for these loss functions, which we must understand which the activation function determines the activation function at the final layer determines the use of corresponding loss function for the whole neural network. Inside, there may be different types of combinations of activation functions, but the activation function at the final layer determines the final type of loss function which we use for our deep learning task. So, to train the neural network means to find values of W and B, of course. It means that we must also select number of layers. Yes, We have the labeled data. We must get the loss function. We must define the loss function, which depends on the type of activation functions, which we use at the final layer. And of course, we must know the so-called optimizer. Optimizer means the modification of gradient descent algorithm. So, because there are many types of, we already consider of many variants of the basic idea of gradient descent is very simple, but there are many modifications with averaging of some moments or gradient is averaged, learning rate is selected adaptively. So, for example, Adam is one of the most popular types of this gradient descent. And nevertheless, but the key feature in all learning algorithms, not only in, I believe, in the most problems for the machine learning, is to proper behavior of gradient descent. How to devise gradient descent. And gradient descent means to calculate the gradient, first of all. And to calculate the gradient, also, as we told, a backpropagation is used. In all neural networks, the idea is that the information, when we make predictions by our neural network, information flows from left to right. But the derivatives, which are necessary for the derivatives by all the W's and B's. For example, here in this case, we have a lot of parameters. Yes, we must multiply. How many parameters do we have here? In the first layer, there are 8. Then plus 8 multiplied 6, plus 6 multiplied 6, plus 6 multiplied 4. So about 100 parameters. About 100 parameters. All these we have to calculate the derivatives for all of these parameters. And this is done by backpropagation. What is the idea of backpropagation? It means that we calculate the derivatives by W and B for the last layer. And then we can recursively calculate derivatives for W and B for the last but one layer. And then iteratively we go to for the second from the end layer. And so on iteratively we get the derivatives of W and B for the first layer. This is the idea. This is a very nice mathematical trick, which is called backpropagation, which is known, I believe, already in 90s, even maybe in late 80s. But it did not get much spreading at the time. It didn't become so much popular. So this is just what we must understand, that the derivatives are calculated in a backward way. It means that they are calculated from the last layer to the first. It may not seem very logical, but it can be substantiated from the mathematical point of view. In this way, we can calculate the gradient. Finally, what I want to say that there are several types of neural network, which of course are not limited to feed-forward, which we have just observed, subsequent flow of information from left to right. There are also recurrent neural networks. In the recurrent neural networks, data not just continues to flow from one neuron to another, but there is also some memory. Each neuron has some memory. And these recurrent neural networks, they were widely applied, for example, for the generation of text generation in generative artificial intelligence, of course, before the invention of transformers, which provide parallel processing of all the data that we have. But recurrent neural networks nevertheless are widely used in many applications. They are more hard to train, although they also use backpropagation and gradient descent, but in some their own specific way. So they are a little different from the feed-forward neural network. Convolutional neural networks, also, which are especially used for the processing of images, they have feed-forward neural networks, which we have just considered as the final stage. But previously, they have some layers of so-called convolution and pooling. It means preliminary processing of information. It means, for example, for images, the extraction of some specific features. So deep learning is known that it generally doesn't require very carefully selective feature generation, manual feature generation. But these features can be learned automatically by the deep learning algorithms. How it is done, what is inside, we most often we do not know. But nevertheless, such architecture of convolutional neural network, which means some two-dimensional filters for the detection of different features, corners, circles, some transitions, etc., is used at the first part of feature extraction. And then once we have a set of features, which is supposed to be less than the number of pixels, for example, in the input image, we can then process them by the feed-forward neural network, which we have just considered. And we have, for example, softmax function as the output to determine to which of the classes this image belongs. So these are convolutional neural networks, very, very briefly. This is called convolutional neural networks, and they're widely used for the processing, especially for images, although I have some experience of applying them also to the classification of radio signals, of wireless radio signals also. They can be quite useful. So, of course, this is just few types of neural networks. What I wanted to mention is, again, feed-forward, which we are considering now during this short review, recurrent neural networks, and which have some memory in each neuron, and convolutional neural networks, which use some two-dimensional filters for the extraction of some particular fragments, or detecting some edges or some sub-objects in the image or another input object. So this is I wanted to say about the basics of neural network. And let us consider our last topic briefly, unsupervised learning. In unsupervised learning, the data are not labeled, as we have already said, and the task is to understand some tendencies in the data without having them labeled. It means that we can do the following three main tasks as clustering, its dimensionality reduction, and anomaly detection. For clustering, this means to divide data into some clusters, which are not labeled, but we can select, we may try to select several typical classes of data. The most frequently used algorithm is so-called k-means. K-means means that we are repeatedly perform two operations: assigning of all data points to two preliminary randomly selected points, centroids, in the case of two classes, 2 points, or in the case of k classes, k points. Then we assign the points, then we recalculate the central point, centroid of this class by taking the average of all data points of this class. Then we again assign all the points again from the scratch, from the very beginning, without no memory. We again assign all the training point, all the data points to each of the centroids. Then we again, after this assignment, recalculate the centroid, and this iterative process leads us to the several these centroids, the desired number of centroids, which optimally represent all the data points. For example, in this case, we have two data points which are supposed, in the lower right corner, two data points which are supposed to be the most typical representatives of all our data. This is the idea of k-means algorithm. The cost function, the average error of such approximation of all the data set by 2 points, decreases, or at least does not increase, with the growth of iterations. So this is a very important feature of k-means algorithm. Of course, also we know that very careful initial approximation of these data points should be taken. Sometimes several random initial approximations could be selected. So because k-means algorithm, cost function of the k-means algorithm may have many local minimums, and so we may try different initial approximations. For example, randomly taking some points, or randomly selecting some elements of the data as centroids. Yes, and we have already observed it also in the lesson dedicated to the unsupervised learning. So this is the idea of k-means algorithm. Also, sometimes the questions rise to what is the proper number of classes which we should use. In each application, it could be different number of classes, maybe 3 or 5 here in the selecting the proper number of short sizes. And did I have this image? No, I should include it. We observed also, where is this example? Yes. For example, some elbow, two approaches are possible, elbow and silhouette. Elbow, when we are looking at the number of cluster, when the final change in our cost function, depending on the number of clusters occurred. We calculate errors for each number of clusters, and we plot it as a dependence of this mean error depending on the number of clusters. And the point where the last change occurred is called elbow. It's probably the number of clusters that we should choose. Silhouette is more sensitive. Yes, for example, in this case, which also we considered when the data, we have 4 classes of data. It is supposed, it's calculated, this silhouette parameter is a byproduct of K-means algorithm. And it's here, it shows us that probably there are 4 classes in our data, although it may not always perform well. But in this case, it produces that it shows us that there are probably 4 classes for our data, which is confirmed by the visual observation. So, also, yes. As for selection of outliers, yes, in data, we may have some non-typical data points. So how can we select them? We know that most of the processes in the nature and in the outside world can be modeled by Gaussian distributions. And Gaussian distribution is famous for its 3 sigma rule, that most of the data points are situated within the 3 sigma range, around the mean value of all the data. Well, based on it, we can assume that the data points which are outside 3 sigma range can be outliers. Yes, for example, like in this case, we mark here these 3 sigma boundaries, negative and positive, and the data points outside of it are possibly outliers. So here it's also depicted in the dynamical way. So we have about 1,000 data points, and the outliers are the points which are situated outside the 3 sigma. But when our data does not have Gaussian distribution, another way is to analyze the probability density function, which is the same as histogram, in fact, and we may select some threshold for the probability density function. And the data points which correspond to the threshold, which have, in other words, which have the sufficiently low probability, can be supposed to be outliers. Let us say it in this way. Yes, with probability density function is sufficiently low, they can be supposed to be outliers. And of course, there is a question how to select the threshold. And we can use, for example, the well-known, already mentioned here, parameters of precision and recall. And the threshold with the highest F1 parameter could be selected as a best threshold for the with which the value of probability density function will be compared. So we can try different thresholds, as we observed in the example, practical example, and we select the threshold with the highest parameter F1. So if we want, for example, we can, but as if the data were Gaussian, we can calculate mu and sigma, build the probability density function like it was Gaussian, and set up threshold. This is the general algorithm for outliers detection. It works for one-dimensional way. Also, we can see here how we can define decision boundary for the two class for the case of two parameters, like here, for the some server network, two parameters through output of megabits per second and latency in minus milliseconds. We can define some decision boundary which corresponds to the intersection of three-dimensional probability density function with a plane. This horizontal plane on the left corresponds to the selected threshold. By maximizing F1 parameter of classification, we can get corresponding decision boundary on the plane of x1, x2. Yes, in this case, it's ellipse, like ellipse, this decision boundary, and the points outside this decision boundary are supposed to be outliers. This is also how we can detect outliers. The last topic in this unsupervised learning. So we have already talked about clusterizing, outliers detection, and dimensionality reduction. Yes, in some cases, like here shown on the paragraph, on the picture, we can move even from three-dimensional space to two-dimensional space, or even one dimension could be enough to characterize some parameters depending on the task which we observe, which we consider. For example, when we have many parameters, maybe only few of them would be necessary for some subsequent tasks. So dimensionality reduction is important. It's especially important in the view of so-called curse of dimensionality, that the problem of performance of machine learning methods may decrease when the number of input features is sufficiently high. It's not always the case, but very often this is a reversal effect of the increasing of number of input parameters. So we may decide to exclude some of the parameters or to go to a new set of parameters which are less in number. This in particular may reduce the effect of overfitting, which we also mentioned. And briefly, principal component analysis means to find a new system of coordinates for our data. Yes, for example, here there are two coordinates and the data represented by these two coordinates are quite correlated. And we can substitute them, maybe these two axes, x1 and x2, just by one axis. This is the idea of principal informative component. We can select also, not to lose any information, we can select the next component, next axis, as a perpendicular to the first new selected one. And this new set of coordinates may be calculated by the means of linear algebra. In fact, these new axes are the eigenvectors of the covariance matrix of the input data, which we have. We can calculate covariance matrix and select these new axes as the eigenvectors of the corresponding covariance matrix. This is called singular value decomposition of our data. So, and of course we have eigenvectors, and original data can be uniquely reconstructed, by multiplying the obtained new set of data in U axis by the transposed matrix U, which is composed of eigenvectors. But if we exclude some of the columns of this matrix, we still can go to the original data, but with a few number of components. And we leave only those components which correspond to the highest eigenvalues of the covariance matrix. Other sufficiently low eigenvalues and the corresponding eigenvectors can be given up, can be thrown away. So we can come again to our original data, but with a less number of coordinates. This is the idea of principal component analysis. We have observed how, for example, for images 30 by 30 pixels, we can get different qualities of approximation of these digits from NIST database, for example, using different number of principal informative components. And for example, for 200 or 250 components, we have almost the original representation of the data. Also, we considered this eigenphase feature. Also, we compress data about 6 times. So by implying also principal informative components. So again, yes, it's essential. Again, it's essential for principal informative component analysis that the data should be pre-processed to have zero mean. Also, outliers should be desirably excluded. We also calculate covariance matrix and calculate its singular value decomposition and select the optimal number of principal components. And means to leave those components which have sufficiently high eigenvalues. It means that we preserve only the eigenvectors with sufficiently high eigenvalues. It means that those eigenvectors are preserved which contain the most important information about the original data. Remaining eigenvectors probably represent some noises or minor features of the original object. So in this way, principal component analysis, powerful mathematical technique, linear technique from linear algebra, which allows us to reduce the number of components. Well, thank you very much for your attention, for listening to this short review of the basics of machine learning course.